Hello, everybody. My name is David Soldani. I've been active in the ICT field for about 25 years. I've contributed both as an academic as well as an industry player. As an industry player, I've served Nokia Huawei for about 25 years. And now I'm currently with Rakuten, and at Rakuten, I've contributed as the Chief Information Security Officer for Rakuten Symphony. And I'm currently running a division at Rakuten Mobile, looking into innovation and advanced research. As an academic, I'm still active, and I'm an adjunct professor at the University of New South Wales. And through this time, I had a chance to go deep into the wireless technology, network technology, Open RAN, cybersecurity, artificial intelligence. I said during the last 3 years, I've been particularly mindful and interested into digging into the cloud native architectures and technologies. So today I'm going to present my views on the path to 6G. I will then introduce you what eBPF is, some applications on the Kubernetes platforms, and then an introduction to our Sauron eBPF platform and some conclusions. So where are we today in terms of network deployments, virtualization, and network disaggregations? So we speak at Rakuten Mobile, we have already deployed an end-to-end, fully virtualized and decoupled infrastructure. And the benefits that we have achieved with respect to traditional implementations are clear, especially in terms of cost reductions. And we have achieved 40% CapEx reduction as well as 30% of OpEx reductions with respect to what we would have had in place if we had implemented, say, a monolithic approach to mobile communication systems. So what's next? Next is around introducing automations, and projects like Nephew are aiming to making Kubernetes the de facto standard for declarative management within the telecom by establishing common templates that conform to both the O-RAN Alliance specifications as well as 3GPP specification for automation, configuration, and management. You may think of automation of cloud infrastructure resources, automation of workloads, deployments, and then workload configurations, workloads meaning virtual network functions. So it's now time to shift from this enhanced traditional way of deploying virtual network functions to something that needs to be cloud native and secure by design. So I am expecting here that 5G will be cloud native. So we will talk only about cloud native functions with an easy way to deploy them on Kubernetes and related plugins and evolutions thereof. And the network infrastructure will be powered by eBPF. So eBPF simply let you run custom code in a kernel when the kernel and application passes certain hook points. And I believe that eBPF has the potential for networking, observability everywhere across the infrastructure, and security assurance with an improvement in terms of quality of end user experience. And my expectation are that eBPF will be massively employed across the whole infrastructure, not only on ground, but also near and on space, thinking at the employment of eBPF on satellites, particularly the regenerative satellites. So this figure is a representation of a reference architecture for 6G systems. I also believe that eBPF will play a pivotal role into the DevSecOps processes, and particularly will be massively employed for runtime security. Now, a couple of words about eBPF, and we may start from the definition. What is eBPF? So eBPF stands for Berkeley Packet Filter, but it is far beyond that. You may think of a general purpose engine or a sandbox virtual machine in the Linux kernel that allows you to run programs in the kernel, now also on Windows, and instrument the kernel behavior without changing the kernel source code or introducing any harm to the kernel stability. There are a number of frameworks we can use for writing and uploading eBPF programs into the kernel. We are having BCC, that is a compiler, Blamby, Rust on IR, or then there is a number of libraries available, or Go, Cilium, eBPF. And currently, the main applications are in the security domain. So you may think of security tooling, observability, networking, tracing, and data profiling. So as I said, it is far beyond a packet filter or something related to tracing. It provides really a novel way of achieving runtime security. Any sort of observability you're interested in, and then enhances the performance of the networking stack. How does the eBPF program work? You may think of two phases. So we do have a deployment phase and a runtime phase. So during the deployment phase, you need to write your eBPF programs using C or Rust, so very low-level languages, and compile them into something that is understandable by the kernel, that is eBPF bytecode, and then load your programs into the kernel using system calls, and at the same time, you need to create maps, eBPF maps. That could be hash tables, that could be arrays, ring buffers, and so on, that will allow the communication between the user space, so your agent, and the kernel space, naming your eBPF programs. During the runtime phase, the eBPF program is verified and then compiled into machine native instructions. And then the eBPF program is attached to the desired hook and then triggered once a particular event has occurred. In this case, you may see that the program is attached to the sockets, or could be attached to the TC ingress or egress hooks. And then the eBPF programs simply provide visibility between the kernel and the user space using eBPF maps. So we do have two main categories of eBPF program types and attachment types. So the attachment type defines more specifically where the program gets attached. So the first type of eBPF programs are tracing or perf, and those particular programs are used to provide an efficient way to report trace information about events into the user space. In order to achieve that, there are a number of hooks into the kernel. For example, you may use kprobes, fentry, fexits, trace points, few probes, if you think of attaching your program to the entry and exit of user space functions, and then LSM APIs, which are treated like tracing programs, but using the LSM APIs, you may get a value that affects the way the Linux kernels behaves. So there are basically security checks you can make use of. Networking means that your eBPF program types will be used for processing network messages, and with those will allow you to customize the networking behavior. Typical hooks are the socket filters, and then traffic control that provide a custom filter and classifier for the network packets for both ingress and egress traffic. Or you may think of using the XDP, so the Express Data Path. In this case, XDP, if supported by the network device card, you have that the CPU is basically offloaded by your programs. And then the C groups, those are C groups, control groups, are for restricting the set of resources a given process or processes can have access to. And for example, the C groups are used as a mechanism to isolate one container from another on your platform. So why eBPF? There are three main reasons why eBPF has become so popular, and it will be massive deployed in the near future. So as I said, it shows amazing programmability without harming the Linux kernel and in real time. And then brings visibility, control, and performance across the whole infrastructure. As with eBPF, we have our ability to trace pretty much anything, any aspects of the system, as all your containers and pods run on a single host operating system. It has a very high performance in terms of networking, and then provides us an instrument for real-time detection responses to any sort of potential threats, thinking of, for example, unauthorized access to your platform resources. Extremely low overhead, as we can avoid the utilization of sidecars, or when we think of offloading the Linux traffic through an XDP direct path from your network interface cards to your containers or pods. So we say that eBPF is to Linux kernel, and nowadays also to Windows, what a JavaScript is to the web browsers. Some examples of eBPF applications to Kubernetes, and here I'd like to give the credits to our friends from Isovalent, particularly thankful to Thomas Graf and Litz Rice, who have made available a lot of content and material on internet, to which I'm now referring to. Starting from the networking, you may see here on this slide how the Linux networking stack is really simplified with the use of eBPF. Now looking at the node networking, you do have the Linux networking stack rather convoluted, which needs to be then identically, it is practically identically repeated to bring connectivity to your applications within your pod, and therefore you will have an overhead exactly with the same characteristics to allow the communication between the network interface cards and your pods. And that could be dramatically simplified with the use of eBPF, and it is Isovalent has proved, has demonstrated that performance in terms of Linux networking can improve a factor to 4 with respect to traditional IP tables implementations. And also The operations will no longer be linear with the number of the entries of the IP tables, but will simply scale regardless of that. So with eBPF, we achieve an amazing way of providing load balancing within your cluster, and it's basically the faster way of doing it. And this is achieved by using the eBPF maps. Like you see here, your cluster IP can be mapped directly onto ephemeral IP addresses or pods using particular ID, and therefore making extremely fast the communications between exposed port and the corresponding pod. Also thinking of service mesh and the way you're handling application traffic using service mesh proxies, so namely subcars. Using eBPF, it is possible to reduce the number of proxies needed to achieve a service mesh from N, which is basically the traditional implementation, thinking of deploying plugins such as Istio, down to no proxies or a single proxies if really it is certain functions are needed for achieving the desired service mesh. Then thinking of bringing the cryptography into the infrastructure through eBPF, it is possible to avoid the utilization of sidecars, as illustrated on this figure. Those functionalities in terms of achieving the authentication, encryption, the communication between pods may be implemented using eBPF, thus avoiding the utilization of sidecars and get the best out of it, thinking of what you could implement into the network layer with what practically you would achieve through the introduction of subcars into the user space. Security and runtime security is really enhanced. It allows us to shift from asynchronous notification to basically synchronous way of killing malicious processes or behavioral applications that adversarially to your system. So if you think of implementing the user space, your rule engine, what happened here once the kernel probe detects a malicious attempt and reports that to the user space, you still allow enough time to achieve, say, the harm into your machine, because this malicious activity may continue within this time interval from, say, action to reaction. Whereas if you're using tools such as Tetragon that runs in the Linux kernel using eBPF, it is possible in real time to detect this malicious behavior and then enforce the corresponding actions, such as killing that particular process that has malicious behavior. Now, we have also extensively worked on eBPF, and we have built our own platform that we have named Sauron. We have also published a 30 pages paper that goes and details our implementations and what we have achieved in this domain. So Sauron, it is in eBPF platforms. This is our architectures. So we support a number of agents, so daemon sets. We do have a way of controlling them centrally, including the introduction of machine learning applications, thinking of various use cases. for example, to achieve massive observability, including energy, not only traditional performance indicators, counters, or gauges, security, and networking across different type of devices. We do have ability to attach eBPF programs all over the places, from uprobes down to the XTP traffic control hooks, kprobes, anything that basically it is linked to the specific use cases we want to achieve on our RMI network. This is an example of the architecture that we have implemented, thinking of observability. So node agent, ability to control thousands of agents on our network. And then you see here the exchange of information through eBPF maps and the various programs that could be attached, in this case for observability, to virtual Ethernet ports, as well as the system calls or the XDP hooks. As we speak, we are testing our solutions, our models in a sandbox, and then the next step is to bring in productions our solution on any sort of device, end-to-end, and the use cases we have demonstrated technical feasibility and business availability of our solutions are examples, for example, like shown on this figure here, that we have shown how eBPF can be used, deployed on routers to avoid possible incidents that may be caused by too large files on routers. We also have ability to deploy our solution on any sort of routers, so that by generating synthetic packets, we have ability to measure hop by hop and end-to-end latency, packet losses, jitters, and quality of service. We also have applied our solution to measure the energy consumed by different type of pods applications running on Kubernetes. Then we have demonstrated ability to extract packets between interfaces of the radio access network and the core network, and produce in real time gauges and sort of counters, for example, to measure latency and time required to establish a session end-to-end from a mobile terminal to the core network and back. And then we have also demonstrated ability to tap all over the places into the virtual network infrastructure. And now we have a strong focus on runtime security, which is not limited to developing eBPF as a sort of information, but we are also developing machine learning algorithm, for example, detecting anomalies and preventing unauthorized access in real time. Now, I would like to show you a demo, a simple demo that we have made thinking about energy. And the demo here runs on GCP, so on a Google Cloud platform. We have 5 virtual machines on which we have installed 5 nodes. So we do have a master node and then 4 worker nodes on which we ran a core network, a 5G core network, radio access network, and a few mobile phones. So like you see here, on this
what you see here is the energy dashboard of Sauron
graph, you're having ability
the Kubernetes
to
cluster of our
capture
testbed is hosted
the
on GCP, and it
power
has one
that is
master node and 4
dissipated
worker nodes.
within each
At the top of the
place,
dashboard, we can
but
see the total
also
energy consumption per domain.
we have
The
ability
unit
to
here is kilowatt hour per.
capture the
for
energy
the
which
5G
is
core and the 5G.
used,
We
consumed
have
by
also
any
SMF.
by any pod. So like look at the core network, we know how much energy the UPF consumes, how much it's taken by the AMF, SMS, all functions. So this basically provides us ability to get to know which part of the network is more costly in terms of energy consumption, and which part of the virtual network infrastructure could be, for example, put to sleep, so like switched off for us to reduce the costs across the 1,000 clusters we are having in production. We also show the ability of the system to detect in real time how the power dissipates, and this is the case where we have increased the number of terminals. As we increase the number of terminals, all functions they get active, and we can measure exactly the corresponding energy consumption variation. So in conclusions, I would like to invite you to read our works. We have made available in high-level paper this year that was presented for our Congress, but also we have published comprehensive detailed work on what we have achieved with the Sauron, thinking of a new approach to the cloud-native observability, networking, and security for current networks, thinking of 5G, 4G networks, and also for the future networks such as 6G. So in conclusions, I do believe that we need to build on the existing network architecture and thinking of the decoupling and the way of segmenting the various domains, disaggregating the infrastructure, because definitely that is a solid foundation for the development of 6G. And we need to really make this next generation network cloud native and secure by design. And we also believe and want to collaborate with our partners. So with that, we have an ecosystem of players to look into new use cases. For example, thinking of logistics, smart factory, drones, or other type of applications across the many vertical sectors. And we are empowering a secure and cloud native ecosystem with a collaboration with Rakuten Symphony, and promoting a secure and robust 6G ecosystem powered by eBPF. I hope I gave you some insights into this powerful enabling technologies. We can stay in touch, and you may reach me on LinkedIn. Here you're having my LinkedIn address, or you may contact directly to my using my business email. There are also a number of references. So with the team, we published and made available publicly many documents you may use to learn more about cloud native architectures, technologies, and particularly exploring and making use of the powers of eBPF. Thank you so much, and let's stay in touch. Goodbye.